All right, today we are diving into something, well, truly groundbreaking in theoretical physics. We're looking at a brand new paper from Alexander Ngugu and Amaya Odilon Koso. And what they're proposing is a unified theory of everything. But here's the twist. They're not doing it by dreaming up extra dimensions or weird new particles. Instead, they claim to have found a shared language, one that's been hidden deep inside the very laws of our universe all along.
So, why do we even need a theory of everything? Well, it all comes down to this. For about a century now, physics has been living with a deep, nagging contradiction. See, we have two sets of rules for our universe. On one hand, you've got Einstein's general relativity. It's beautiful, majestic, it perfectly describes the big stuff. Planets, stars, galaxies, all gliding through the smooth, curved fabric of space-time. But then, on the other hand, we have quantum mechanics, and that's the rulebook for the tiny, bizarre world of atoms and particles. The problem? These two theories are completely incompatible. They don't just disagree on the details. They describe two fundamentally different realities. It's like they're written in different languages, and that's a huge problem, because they can't both be right, at least not the whole story.
Okay, so here's our game plan for unpacking Gu and Koso's solution. We'll start by really digging into this great divide in physics, then we'll get into the brand new cosmic language they've come up with. After that, we'll see how it all comes together at the Planck scale. We'll also look at how this new idea might solve some age-old paradoxes, and maybe most importantly, we'll see if it's a theory we can actually go out and test. Let's get started.
So let's really get into this core problem. Think about general relativity. It paints a picture of a universe that's like a perfectly crafted Swiss watch. It's smooth, it's continuous, and it's deterministic. If you know where everything is now, you can calculate exactly where it will be in a billion years. It's clockwork. But then, you zoom way, way down, and you hit the world of quantum mechanics. And it's not a Swiss watch at all. It's a chaotic casino. Everything's fuzzy, it's jumpy, and it's all based on probability. You can't even know for sure where a particle is and where it's going at the same time. So you've got this clockwork universe and this cosmic casino, and they just don't fit together.
And this is really the heart of the matter. You've got Einstein's world, elegant, where gravity is just this gentle curving of a smooth space-time fabric. And then you've got the quantum world, where reality isn't a fabric at all. It's more like a pixelated screen, a jittery, buzzing collection of pure potential. Now, most of the time, this isn't a problem, because they operate on totally different scales. But what happens when you need both? Think about the center of a black hole, or the very first moment of the Big Bang. That's a place that is both incredibly massive and incredibly small. And when you try to use both sets of equations there, well, they just completely break. The mouth spits out nonsense, literally infinities. And that's a huge sign that we're missing something fundamental.
So how do you bridge this gap? How do you get the clock and the casino to agree? Well, this is where Ngugu and Koso come in with a radically different approach. They're proposing a whole new cosmic language, a framework they call Delta Infinity Omicron. You'll see the symbols in a second. And their big idea is this: maybe reality isn't about states, what things are, but about transformation, what things are becoming. And this new language is designed to describe that exact process. Okay, let's break down this new language. First up, we have delta. You can think of delta as, well, the starting point. It's the universe as pure, raw potential. This is the quantum world in its natural habitat, a shimmering sea of possibilities. A particle isn't here or there. It's everywhere at once, existing as a wave function, a superposition of every possible state it could be in. It's like the universe holding its breath before it's made a choice.
And on the other end of the journey, we have Omicron. If delta is the question, Omicron is the answer. This is the end point. This is the reality we actually experience, the one we can see and measure. It's the world where that particle is now right here, not spread out in a wave of possibilities. This is the classical world of Einstein, governed by definite spacetime, clear cause and effect, and gravity. This is reality made real, actualized.
So you've got the start, delta, and the finish, Omicron. But how do you get from one to the other? That brings us to the absolute key, the heart of this whole thing, the infinity symbol. Think of this as the engine of creation, the bridge that connects the quantum world to the classical one. It's like a cosmic Rosetta Stone. It takes the strange probabilistic language of quantum possibilities, delta, and it translates it into the concrete, definite language of the reality we know, Omicron. It's the process itself. It's what turns maybe into is.
Now, to make this idea really click, the authors give us this fantastic visual metaphor. They call it the general relativistic principle. Just imagine you start with a simple triangle. It's got sharp corners, straight lines. It's kind of clunky, right? Let's say that represents the discrete, jumpy quantum world, our delta. Now, what happens if you add another side? You get a square, then a pentagon, a hexagon, and you just keep adding more and more sides. As the number of sides gets bigger and bigger, approaching infinity, what happens? The polygon starts to look less and less clunky. The edges smooth out, and eventually it becomes a perfect, continuous circle. And that circle, that's our smooth, classical world of Omicron. The process of adding all those infinite sides, that's the infinity symbol in action. It's a beautiful way to think about reality as this constant process of smoothing out.
Okay, so this new language, this transformation from a triangle to a circle, it's a really cool idea. But is it just a nice story, or is there real physics behind it? Where's the proof? Well, this is where it gets really interesting. Ngu and Casso argue that if you look at the absolute smallest possible scale of the universe, what's known as the Planck scale, the two languages of quantum mechanics and general relativity aren't just similar, they're literally forced to become the same thing.
So the Planck scale. This is where the fundamental constants of nature all meet up for a party. You see these equations? You've got h bar in there, the reduced Planck constant, that's the soul of quantum mechanics. You've got g, the gravitational constant, that's the rule book for gravity. And of course c, the speed of light from relativity. These numbers aren't just random, they are the bedrock of our universe. And when you combine them in just the right way, they define a scale of length, time, and mass where quantum effects and gravitational effects become equally powerful. This isn't just a convenient place to look, it's the only place where these two theories absolutely have to talk to each other.
Okay, get ready, because this is the core of their mathematical proof. Let's look at this from two directions. First, from the quantum side. You've got Heisenberg's uncertainty principle. You know the one. The more you know about where something is, the less you know about where it's going. And it sets a hard limit. If you try to pin down a particle's location to the size of one Planck length, its momentum becomes wildly uncertain. Now, let's look from the gravity side. General relativity tells us that if you cram enough mass into a tiny enough space, say a Planck length, you create a black hole. You get an event horizon, a point of no return. And here is the absolute kicker. Ngu and Casso show that the amount of mass energy you get from that quantum uncertainty is the exact same amount you need to create a black hole at that same scale.
And that leads to this beautifully simple conclusion. Now, I know what you're thinking, it just looks like something equals itself. But don't be fooled by the simplicity. The power here is where those two sides came from. They came from completely different theories, different worlds of physics. One is about the limit of our knowledge, quantum uncertainty. The other is about the limit of physical reality, gravitational collapse. And yet, when you push them to the absolute extreme at the Planck scale, they give you the exact same answer. Why? Because they have to. Because at the most fundamental level of reality, they are not two different things. They are two descriptions of the same thing. This is it. This is the point of unification.
Okay, so unifying the math is one thing. That's huge, obviously. But a really great theory, a truly great theory, does more than that. It should also clean up the messes left by the old theories. It should solve the big, stubborn paradoxes that have kept physicists up at night for decades. And that's exactly what the Delta Infinity Omicron framework claims to do.
Let's take black holes, for example. In the old view, general relativity tells us that at the center is a singularity, a point of infinite density, where all the laws of physics just stop working. It's a dead end. But in this new view, there is no infinity. Instead of a singularity, you get a quantum core. Spacetime has a maximum curvature, a point where it can't be compressed any further. The authors have this great analogy for it, a quantum trampoline. Spacetime gets pushed down, stretched to its absolute limit, but it doesn't break. It bounces back. And this immediately helps solve the famous information paradox. Information that falls into a black hole isn't lost forever in some unknowable singularity. Nope, it's preserved in this quantum core, ready to be slowly released as the black hole radiates away.
All right, here's another deep one, the problem of time. This sounds weird, but when you try to write down a quantum equation for the entire universe, like the famous Wheeler-DeWitt equation, the variable for time just vanishes. It's not there. The equation describes a static, frozen universe. But obviously, we experience time passing. So what gives? Well, in the Delta Infinity Omicron view, the answer is that time isn't fundamental at all. It's an emergent property. Remember that transformation from the quantum potential of delta to the classical reality of Omicron? Well, that process, that's time. The very act of the universe transforming from maybe to is what we perceive as the flow of time. Time doesn't just happen, it emerges from change itself.
Look, we've seen a lot of theories of everything come and go, and many of them are beautiful, mathematically elegant, but they're basically philosophical ideas. There's no way to ever prove them right or wrong. And that's what makes this new framework so exciting. It isn't just a dream on a blackboard. It makes real, concrete, falsifiable predictions. It tells us things we should be able to go out and look for, either with the technology we have now or what's coming very soon. This is what takes a theory from being just math and turns it into real science.
So what are we talking about here? Well, the theory predicts that the uncertainty principle we all learned should actually get a little tweak at super high energies. It says we should be able to see faint signatures of this unification hidden in the cosmic microwave background. You know, the afterglow of the Big Bang. It predicts tiny quantum adjustments to the way black holes evaporate. It even suggests that light passing near a black hole might scatter in a weird way, as if it's bumping into a kind of quantum foam texture of space-time. And maybe the biggest one of all, no Big Bang singularity. Instead, a quantum bounce. Our universe might have bounced back from a previous, contracting one.
Let's zoom in on one of these predictions, because it's a great example. This is the generalized uncertainty principle. See that first part? That's the normal Heisenberg principle you know and love, but look at those extra terms tacked on at the end. Those terms are usually so tiny you'd never notice them. But if you get to incredibly high energies, close to the Planck scale, they suddenly become important. And what they imply is absolutely profound. They mean there is a fundamental minimum length in our universe, a smallest possible pixel size. You simply cannot measure anything more precisely than the Planck length, because if you tried, you'd need so much energy you would literally create a black hole. So if we could ever find experimental evidence for this modified principle, that would be the smoking gun.
So, when you put it all together, this theory offers a pretty radical new way of looking at everything. Maybe physics isn't ultimately about finding the smallest, most fundamental thing. Maybe it's about understanding a fundamental process. The delta infinity Omicron framework paints a picture of our entire universe as one continuous grand transformation, a constant becoming, from a sea of infinite quantum potential into the one solid classical reality that we see around us. And that leaves us with one final mind-bending question to think about. If all of reality is a transformation in progress, what's the final destination? What is it all transforming into?